Hi, we are going to evaluate or try to identify the different types of power losses we have in our back converter once we have included the models provided by the manufacturers. In this video, we will focus on the MOSFET and we will identify, let's say, three types of power losses only in that device. Okay, and since it could be a long video, I will split this into two parts. In this one, we are going to see a method to identify and evaluate the three types of power losses, and in the next video we are going to see how we implement that method in LTspice. So let's focus on this device. Let's review the voltage and the current across a MOSFET. Here we have the voltage across a device, and here we have the current through the device. In this part, the MOSFET is off, is blocking some voltage, in our case is the input voltage, and the current is zero. Then we turn on the device here, the voltage is close to zero, is close to a short circuit, and it drives some current. In our case is the inductor current. And then we turn off the device again. Here is the input voltage, here is zero. Let's draw the instantaneous power consumption of that device, which is the product of the current and the voltage. If we do that in the simulation with our new models or in a prototype, we will see something like this. Okay, in this part the MOSFET is off, is close to an open circuit and a very ideal open circuit, so the power is zero because the current through the switch is negligible. So here the power is zero, then we turn on the device, we have a peak, then when the device is on, is driving the inductor current, we see some instantaneous power, and then we turn off the device and we see another peak here, and again zero when the device is off. So we will try to understand why we have these four parts or three parts if we don't consider the parts where we have zero. We will try to identify why we have this, why we have this, and why we have this. Well, the easy part is to explain why we have this part. Okay. In this part, the device is completely on. So in the reality, what we have is not a short circuit, we have the on resistance. And since we have current flowing through the resistance, in our case is the inductor current, we will have some power consumption. And that's why we have this instantaneous power level during that part. Then we will try to see why we have those peaks here. Okay, this one and this one. Let's focus first on the first one, on this one. And here you can see the same waveforms, but with more detail. In this part, we are trying to turn on the device, to turn on the MOSFET. So as a consequence, here the device is blocking the input voltage, and here we have zero. So when we turn on the device, the voltage goes to zero. And in the case of the current, here we have 0 amps, here we have the inductor current value in the transition. Okay, in fact, here is the minimum current value through the inductor. And since we turn on the device, from 0 we go to that level. But as you can see, we have some overlap, which means that we have at the same time current and voltage. It's not a perfect vertical line. Okay, so we have time, at the same time we have current and voltage, so we have this current, this peak in the instantaneous power. And the explanation for the turn off is quite similar if we try to understand this in a very simple way. If we focus on this part, we will see something like this. So when we turn off the device, the voltage across the device rises from 0 to the voltage it has to block. In our case, is the input voltage, and the current falls from the load current, well, in our case, from the current that is flowing through the inductor in that point to 0. Okay, but again we have some overlap here. We have voltage and current at the same time. So if you multiply both waveforms, you will have another instantaneous power peak in the turn off of the device. Okay, so let's try to see a method to evaluate this or to identify the different types of power losses here. So here we have the same instantaneous power waveform but with more details. Here we have the interval in which we turn on the device. Here we have the interval in which the device is completely on, and here we have the interval in which the device is turned off. As you can see, the on time is much higher than the switching transitions. Okay. Well, so we know that in general we can evaluate the power consumed by the switch in this way, the average value of the instantaneous power. So we do 1 over the switching period integral of the instantaneous power evaluated in a switching period. Well, since we know that we have 3 types of power losses, what we are going to do is to split that integral into 3 parts. In this way, we will have the first integral, which is evaluated in the turn-on interval in this part, and that integral is the integral of an instantaneous power. If we do the integral of an instantaneous power, we are evaluating an energy. So this is the turn-on energy. Okay. Then we have another part in that integral, is the integral corresponding to the on interval. This part is this area. That area is another energy, is the on energy. And then we have the last part, the last peak. If we do the integral, we obtain the energy for the turn off. Is this part, and this part. Okay, what we want to evaluate is not energy, is power losses. But if we have the energies, we can evaluate the average power. Because as you can see here, if we take into account the switching period or the switching frequency, here we obtain the average power consumed during the turn on. Here we have the average power consumed during the on state, and here we have the average power consumed during the turn off. The good point is that evaluating energies is very easy in LTspice, as we will see in the next video, because we can plot the instantaneous power, and then LTspice allows us to evaluate integrals. Well, so in this way we can evaluate the individually each contribution to the power losses of the MOSFET. And let me finish with some comments about the relationship between energy, average power, and switching frequency. So, first comment is the energy of the turn on, this one and this one, is constant with the switching frequency. Basically, that triangle that we see here doesn't depend on the switching frequency. Every time we turn on the device, we will have this triangle. So it's something that doesn't depend on the switching frequency. However, the turn on losses, power losses, depend on the switching loss, on the switching frequency, because they depend on the period. So essentially, turn on power losses rise with the switching frequency. Basically, because imagine that we turn on the device here, but well, we have some time, we turn off the device, and then we turn on again here the device, and well, sometime we turn off the device and we turn on again the device. So the energy of each triangle is the same, but the average value is higher because we have more triangles per second. So in summary, energy of the turn on is constant with the switching frequency because it depends on the characteristics of the devices, but the power losses related to the turn on process, they depend on the switching frequency. If we increase the switching frequency, we will have more turn on losses. The process with the turn off is very similar. The energy of the turn off is constant with the switching frequency, but the power related to the turn off process rises with the switching frequency. Basically, we have this triangle. If we repeat more times that triangle, means that we increase the switching frequency. We turn off the device more times per second, we have a higher average value, we have more power related to the turn off. And the last comment is the power consumption related to the on state. During the on state, we must take into account the on resistance and the inductor current, but that power doesn't depend on the switching frequency. This is something very obvious, but what is not always considered is that the energy during the on state is not constant with the switching frequency. Okay, the power is constant, the energy is not constant. Basically, because imagine that I turn on my device here and I turn off my device here. The purple area is smaller, okay? But then I turn on again, I turn on again, okay? So if you evaluate the average value, is the same. Power losses due to conduction process are the same, but energy due to conduction process is not the same. Okay, in fact, it falls with the switching frequency. So with this, we finish, and in the next video, we will see how we evaluate this in LTspice. So, see you.